Hello there, Mr. Sutton here, bringing you the Pre-Cal Honors 7-3 lesson on parametric equations. In this one, we will be finding vector equations and parametric equations for a line given some information, and we will also convert parametric equations into rectangular form, which will allow us to identify which conic sections we're dealing with. As a real-life application, we'll figure out how far a hang glider will travel. To see what parametric functions are like and to see how they might be useful in real life, we're going to dive right in with this warm-up. Let's say you jump off a 700-foot building in a hang glider, and every second you're gliding down 5 feet and forward 10. We want you to express your horizontal distance from the building, which we'll call x, and your height, which we'll call y, as functions of time. So pause the video and see if you can do that part of the warm-up. All right, so for x, we're going to write x of t equals, now to find my horizontal distance, since I'm gliding forward 10 feet, I just have to multiply 10 by the number of seconds. So we can write x of t equals 10t. Now for y of t, our height, well, we can't just write minus 5t, although that's a good start since we're gliding down 5 feet for every second, because we're also starting 700 feet above the ground. So we actually have to do y of t equals 700 and then minus 5t. So these are our two equations. These are parametric equations here. But now we're not quite done. We wanted to know how long will it take you to reach the ground and how far will you have gone at that point. So pause the video and see if you can figure out this piece of it. All right, so for how long, we're talking about our height, so we need to use the function that has y in it. And we want to know specifically when y is 0. We want to find the t-value that makes y come out to 0. So I'm just going to write 0 equals 700 minus 5t. And then we can solve for t. So if we add 5t to the other side and then just divide both sides by 5, 700 divided by 5 is going to be, let's see, 140. So 140 seconds. For the next part of the problem now, we want to know how far forward we will have gone. Now we're talking about the x function, and we want to know the value of x when t has a value of 140, because that's the time at which we hit the ground, or hopefully land smoothly. So we're going to be doing x of 140 equals 10 times 140, which is going to give us 1,400 feet. So that's a real-life example of parametric equations. Now that we've got that under our belt, it's time to take off and do the rest of the lesson. At this point, we're going to officially define what we just did in that real-life problem. We were working with something called parametric equations. A parametric equation gives you the location of just x or y as a function of time, or some other third variable. And you can define all sorts of functions parametrically. A line is probably the easiest one to define with a parametric set of equations. So for the parametric form of a line, given a starting point, which we'll call x0, y0, a horizontal vector, which we'll call a, so that's how much you're changing horizontally every second, and a vertical vector, which we'll call b, that's how much you're changing vertically every second, we can write the following. So we can write x of t, or just x, equals your initial x value, x0, plus the time times your horizontal vector a. And we can do the same thing for the y version of this. We can write y equals y0 plus, still using time, but now we're multiplying time by the vertical vector b. So this is the parametric form of a line. They all have this kind of format. Now we can actually put these together into one big equation, which is called a vector equation. This gives the location of a whole point, x comma y, based on a starting point and a direction vector. So if we want to have the vector form of a line, we're essentially just putting this all together here to write x comma y, so we're getting a whole point now as an output, equals our starting point of x0 comma y0 plus the time times, now we're actually going to have a two-dimensional vector with a and b as the two parts of it. So we're going to do a couple examples with linear vector equations and parametric equations. So let's say we want a vector and parametric equations for a line that goes through 2, 6 and has a direction vector of 5, -3. Now the general format for all of these linear vector equations is going to be x comma y equals your starting point plus time times your direction vector. So pause the video and see if you can express that. All right, so we've got x comma y equals, we have a starting point of 2 comma 6 plus t, because that's the only variable, and then we've got the direction vector 5 comma negative 3, like so. Now to get the parametric equations, it's actually much easier if you're starting with the vector equation. For parametric equations, we're just going to rewrite our vector equation with just one variable and time. And by one variable, I mean the numbers that go with one variable. So for example, we could write x equals 2, that's the starting x value, plus t times 5, that's the x vector. So we could write then 2 plus 5t. Pause the video and see if you can write a parametric equation for y. All right, so for y, we've got y equals the starting y value of 6, and then we'll have minus 3t. We're going to do one more example, finding a vector equation and parametric equations for a line, this time one that contains 2 points, 3 comma 1 and negative 4 comma negative 4. So let's assume that 3 comma 1 is our starting point. But how about the direction vector? Because they didn't give that to us. Well, you might remember from dealing with vectors that if you have 2 points and you need a vector, you just have to find the component form, doing second point minus first point. So that's what we'll be doing here. Direction vector will just be the component form for 2 points. Pause the video using this and see if you can write the 2 types of equations here. All right, so for the direction vector, we've got the component form, which will be negative 4 minus 3, comma, negative 4 minus 1. So our direction vector then is going to be negative 7, comma, negative 5. And then for our vector equation, we have the starting point 3 comma 1 plus t times this direction vector that we just came up with. Now for the 2 parametric equations, we have x equals 3 minus 7t, and then we have y equals 1 minus 5t. So you might be wondering what a lesson on parametric equations is doing in a chapter on conic sections. Well, this is where it all comes together. For the next few problems, you're going to be writing parametric equations in rectangular form and then identifying the shape, which will be one of your 4 classical conic sections. So the basic idea on this is you're starting with a pair of parametric equations, and you're trying to use substitution to come up with an equation that has x's and y's instead of t's. So we want to go from 2 equations with t's to 1 equation with an x and a y. Pause the video and see if you can figure out how to do that in this situation. All right, so there's a few ways you could have gone on this one. Probably the easiest, since x and t equal each other, is just to substitute x for the t over in this second parametric equation. So instead of writing y equals 5t squared, writing y equals 5x squared. And then what kind of shape is this? Well, since we only have one squared variable, this is a parabola. So, I mean, obviously they're not all going to be this straightforward. You might have to move things around to get t by itself, but the premise will be pretty much the same in this kind of a situation. This next problem is the same idea, but actually completely different, because you'll notice in this one our parametric equations both have trig functions in them. So if you're thinking this is probably not the equation of a line in parametric form, you're right. It's probably not a parabola either. So what do we do with these trig functions? Because if you're trying to isolate t, it's just going to be a big mess. So to do these situations, when you have trig functions, I like to start off by first rearranging each equation so that I have a squared trig function on one side. So for example, let's start with the x's here, and then you can do the y's on your own. So for x's, to get the trig function squared, I first want to isolate the trig function. So I'm going to divide both sides by 3. That'll give me x over 3 equals cosine of t. And then I just simply have to square both sides. So on the left side, I've got cosine squared of t. On the right side, squaring everything here, I've got x squared over 9. Now you might be wondering why we did this. This is one where you'll just have to trust me for a minute and do it with sine over here. So pause the video and take that next step and do it with sine. Okay, so for sine, we've got sine of t equals y over 3. And then we can write sine squared of t equals y squared over 9. Now you might be wondering why we went to this trouble of isolating and squaring these trig functions. our very next step is going to be to substitute all of this into a Pythagorean identity. Is there an identity that has cosine squared and sine squared of the same variable in it? In fact, there is. That's our original one. Cosine squared plus sine squared equals 1. So instead of writing cosine squared of t, I can now write x squared over 9. Instead of writing sine squared of t, I can now write y squared over 9. So then I can just rewrite this as x squared over 9 plus y squared over 9 equals 1. So I've accomplished my first objective, which was to put this in rectangular form. Instead of two equations with t's, I now have a single equation with just x and y. Now, what shape is this? Well, since these are the same number in the denominator and these are being added together, this could only be a circle. And just optionally, for those of you who don't like the way this looks, you could multiply everything by 9 and write it like this instead. So just be prepared to see either kind of representation here. They're both correct. We've got one more example for you. Pause the video and see how far you can get on this one on your own. I would use that last example as a guide. All right, so for this one, just like before, we are going to isolate the trig functions and square them because down the road we want to plug everything into a Pythagorean identity. So if we want to do that with the x's, that's going to be x plus this 5 and then divided by 2 equals tan of t. And we'll go ahead and square this now. So that's tan squared equals x plus 5 squared over 4. I'm not going to expand the x plus 5 squared. I'm going to leave that in that format because that's what it looks like when I have it in normal conic section form anyway. All right, moving on to this next one. Isolating secant, we have y plus 8 divided by 3 is equivalent to secant. And then secant squared of t equals y plus 8 squared over 9. Now we need an identity that has tan squared and secant squared in it. You might remember the identity 1 plus tan squared equals secant squared. So if I do secant squared minus tan squared, that has a value of 1, just based on rearranging that original Pythagorean identity. And now substituting things in, we've got y plus 8 squared over 9 minus x plus 5 squared over 4 equals 1. What kind of conic section is this? Since we have squared things being subtracted, this could only be a hyperbola. This concludes our lesson on parametric equations. Till next time, Mr. Sutton signing off.